Hello, everyone. Thanks. I'm Qiang from University of Sydney. Thanks for having me here, and also thanks for the nice introduction. I'm very happy to share our recent efforts of pushing large-scale distributed key generation and how we make a blockchain a better world. I assume most of you here have heard of the threshold cryptography. For example, like threshold signatures, you have a digital signature, you have one secret split into multi-pieces, and you need a subset of them to put together to reconstruct the original signature. And that's exactly the essence of what Vitalik just mentioned, 2 out of 3 type of thing. And that's what exactly happening at the MPC wallet. But conventionally, threshold crypto was considered mostly in small scale, in-house applications. A cornerstone of threshold cryptography is actually something called distributed key generation. Essentially, it's like a bunch of internet peers. They talk to each other. They jointly create one public key, and each of them going to have the corresponding secret key share. It's very similar to the consensus problem, but with one actual secrecy requirement that if not enough people pulling together, they learn nothing about the root secret. This whole threshold crypto thing is a very, very well-studied area in crypto, but it got recent resurgent attention in the community in the sense that we found many, many more exciting new applications in the blockchain domain. For example, like in order to defend against MEV attacks, people propose that why not just encrypt the transaction, that the whole chain to jointly decrypt the eventual transaction. And also, large-scale randomness beacon is very useful for the consensus itself sometimes, and also for a lot of smart contract applications. Also, threshold crypto has found a very interesting and very important use in asynchronous consensus design, which I'm going to touch a bit very soon, and also in something recently got very popular, blockchain checkpointing. I'm also going to explain very soon. But in all those applications, we are facing a qualitative different setting that we may face like a whole chain scale participants, which we require the scale to be spread to the whole blockchain, which instead of like 2 out of 3 in-house applications. And the immediate problem we get is all the DKG protocols actually are too complicated. No one even bothered to try to implement to see what actually happens. The consequence is that we either go to find a trusted party to split the key and actually, he knows the root secret, which is obviously not a nice situation in the blockchain setting. Or we try to avoid the threshold crypto system and go turn to very exotic tools like generic snark or witness encryption, which cause its own complexity and trust issues. But most of the time, people simply give up and, well, just pay more, right? We don't get the benefit. And one particular example is in the application of checkpointing to Bitcoin. Actually, recently got very popular. The reason is try to harvest the security and the value store of Bitcoin network, try to boost other ecosystems. The idea is very simple. Just try to put a snapshot into the Bitcoin. Simple as that, right? And the most noticeable proposal probably is Babylon. Not only is a paper, that's also a very nice startup pushing out this project. They took a very natural cryptographic approach. Like every validator just sign a snapshot, and they use something called aggregate signature. What does that mean? You take public key signature pairs, you compress the signature part into one, but leave all the public keys there for verification. Well, this sounds very nature, right? And of course, they need someone to eventually do the aggregation and throw into blockchain. But even with this simple and natural approach, because the scale we are talking now is very large, even listing the public key itself going to require a bunch of Bitcoin transactions. What's worse is that you need multiple aggregator in order to throw the transaction, right? Otherwise, what if no one is actually doing the business? What simple estimation you can get is that by doing a reasonable frequent checkpointing for a reasonable scale network like Filecoin, you probably need to cost millions of US dollars just Bitcoin transaction fee, even with the Bitcoin price today, with the crash yesterday. So obviously, Filecoin don't want to pay. So they try to come up with a dream version called the Pikachu, and they want to use threshold crypto instead, not using aggregate crypto. The idea essentially is, what if like all the participants, all the validators in the whole blockchain to jointly create public key again and again, and then essentially they use one single Bitcoin transaction to do this kind of trust chaining procedure. So in this very natural and simple idea, then essentially you only need to pay one Bitcoin transaction for one single checkpoint. That's essentially the best we can hope for, which is obviously great, right? But they have no idea how to do with this scale of distributed key generation when the network size is big. And so that's why they put up a RFP, and we take the challenge to check whether DKG protocol is actually practically feasible when we are talking about blockchain level, blockchain scale applications. And before we dive into the technical details, let's see how bad it is for now. Well, the quick takeaway is it's really bad, because really bad essentially in every perspective. Like you need to pay, in order to generate one single public key, both computation and the communication is massive, and essentially is practically unbearable. But what's the reason for that? If we peel off all the unnecessary complexity of DKG, the backbone structure of DKG is actually fairly simple. Essentially, like every participant generates some secret, and you split the secret into pieces via some kind of secret sharing mechanism. Intuitively, everyone's going to get one corresponding piece, right? And then they're going to broadcast something. Sounds like very simple, right? Like everyone just broadcasts something. And during the reconstruction, essentially, you can view that some kind of summation is happening at the back end. Kind of the root, the final secret, is decided by the summation of a bunch of implicit polynomial summation. So far, sounds pretty simple, right? But what's actually bad here is if you notice that there's something called broadcast. But broadcast channel is actually a very expensive thing in practice. Well, because broadcast channel requires some very strong requirement that even if the sender is malicious, let's say I intentionally send one to Vitalik and send two to Audrey, but broadcast channel can guarantee that they're going to eventually receive the same thing. So if we do it properly, the right tool to use is actually something called the Byzantine Broadcast Protocol, but which inherently going to causing quadratic communication already. But unfortunately, majority of the DKG research simply abstract it out and assume it for free, because it's something distributed computing's job. It's not our job. And even in practice, like for example in the MPC wallet, they just find some trusted party to do the actual delivery. That's pretty bad for practice. Obviously cannot be tolerated in the DKG setting. And also for computation, it's really because of this something here. Something here essentially for the sake of everyone need to validate things that are going on, right? They need to validate that the shares actually they receive are consistent in some sense. Depending on what type of secret sharing they're going to using, essentially they either need to validate the whole transcript, or whenever there's some complaint, they need to validate the repudiation according to the complaint. Again, another scale of a transcript. So in both cases, they need to pay a lot of computation. So from this very simple overview, we can actually see that the root reason why DKG nowadays are so expensive is simply we broadcast too much. Everyone is broadcasting, and everyone has to pay kind of quadratic communication and verification cost already. But now since we are trying to see whether large-scale practical DKG protocols are possible, we cannot avoid to repeatedly using this kind of expensive stuff, right? We have to ask, is it really necessary? We have to break the barrier of this high complexity thing. Well, the first natural step is we try to reduce the number of broadcasts as much as we can, right? But before that, we actually make a very simple but very critical observation, is that for the goal of distributed key generation, eventually the secret is decided by the summation of a bunch of subset. As long as one honest guy secret is actually included, then the final secret will be fine. The issue is, who is honest? I have no idea, right? If I know there's an honest party, I simply go find that guy to do all the job for me. So naturally, it comes to the committee-based idea. We can try to select something called any trust committee. But the key difference here we want to stress is that any trust committee only need to require one party among the committee to be honest, instead of like honest majority. That's very different with most of the committee-based approach. Because if you insist honest majority inside the committee, then the committee size are going to be very large again. And the next question is, how do we actually select any trust committee? We cannot like arbitrarily select some, because if you arbitrarily select some, attacker knows, then maybe launch dedicated targeted attacks, right? Well, the idea is also simple. Why not just choose them uniformly? But where do we get the randomness? If we ask all the validators to run the distributed randomness generation protocol again, kind of we are coming back into a circular situation. The scalability itself is an issue. But thinking now, we are building distributed key generation for the sake of blockchain applications. Blockchains are there. Why not make best use of the existing infrastructure? That's what we simply do. Then we try to harvest randomness or randomness beacon from the blockchain. Then we use it and apply some VRF-based approach to choose the committee in a secret way until when the committee starts sending out message, no one knows who is chosen. And also some other optimizations to leverage blockchain itself as a broadcast channel, reduce on-chain costs as much as we can. But life is not so easy. It looks like whenever we have a committee, everything's done. Unfortunately, there's a general issue here, because whenever we kind of shift the task from a whole chain scale to a small size committee, there's a natural question. What if all the committee actually got hacked? Because eventually, after the committees speak up, then they expose themselves, right? Maybe all kind of network attack can be launched, even just block them speaking. And what makes it worse here is that in the distributed key generation setting, when someone sends a task, like for example, Audrey did broadcast some message, but I intentionally complained that Audrey didn't send me something correct. Originally, Audrey can come to repudiate by revealing whatever she sent before, but now she's attacked. She cannot even prove she's innocent. Then what are we gonna do? We kind of changed the whole design logic in the sense that of insisting on whoever being complained to prove he's innocent, we asked whoever complained to prove that your complaint is legitimate. And in order to do this, we can leverage some other cryptographic tool called the verifiable decryption. Luckily, we don't need to refer to the generic snark stuff. We can use conventional, more classical zero-knowledge proof and efficient zero-knowledge proof, and with some other cryptographic techniques. But still, there are more challenges because most of the blockchain have a lot of stakes. However scalable we are, we cannot afford to treat every stake as one party because the number of stake is massive, right? We have to do some kind of sub-ID allocation in some way. Essentially, we kind of solve some kind of optimization problem to group a batch of IDs together to create a virtual ID in order to reduce the total number of actual ID. And the key thing is that we need to preserve the trust assumption. Originally, if we have certain honest ratio, then we need to be sure that after the grouping or sub-ID allocation, the honest assumption preserves. It's kind of constrained optimization problem in some sense. And with all those things together, we can finally have a protocol and do some careful evaluation. And the theoretical evaluation actually is very simple because we essentially minimize the number of broadcasts to essentially minimal, right? And if broadcast itself is kind of metric to be captured for efficiency of DKG protocols. But what matters more, I guess what interests more here is actual practical evaluation. We also implemented this, prototyped the system and did some tests. If the concrete number does not matter much, but at least we can see some hope, right? Originally, based on the estimation, even if the local computation alone might take hours, now we can push it down to something like within 1 minute. The actual computation is only 2 seconds. So at least show our practical hope. So with the major component DKG done, then we can with some a bit more optimization, then we can actually enable all hands checkpointing to realize the dream of a Filecoin, like Pikachu. Then they can essentially checkpoint Filecoin to Bitcoin, paying only 1 Bitcoin transaction fee for one checkpoint. And obviously, Marco was a bit happy. And our paper is online. If you are interested, you can take a look at the details. And of course, along the way, we also advanced a lot of DKG theory itself by removing all kinds of practical considerations. But this one is the most practical one, so maybe we put more optimizations on. And since DKG is actually can enable a lot of interesting applications. Besides advancing DKG itself, we are also exploring other potential applications. One very natural application is we try to eliminate the bias in Ethereum randomness generation, like Rondo. Well, naturally, we're going to leverage the power of distributed key generation, but the difficulty is Ethereum is even larger scale. We need to make it using even more refined techniques to make it even more scalable. And what's more interesting is that because Rondo currently even want to deal with a very, very extreme situation like dishonest majority, well, DKG obviously cannot handle that. But we can combine the technique together in the way that even the extreme thing happen, we can behave exactly like Rondo now. To quickly reflect, when we consider constructing or building a large-scale distributed computing or cryptographic protocols, many things cannot be assumed for free. We have to open the box, or we have to look into every possible component to minimize all this heavy stuff. But on the positive side is that the whole chain scale threshold crypto is actually practically feasible. Well, I'm not saying it can be deployed tomorrow, but like the 1 minute or maybe a few seconds delay at least show a strong sign of practical feasibility, right? What I would like to stress more is that threshold crypto is actually so simple and so useful. We should definitely not avoid using it because it looks complex and using something more exotic. We should definitely explore more. One very notable example is I just promised. We actually make a critical use of threshold signature, generate all kinds of interesting proofs that we push something called asynchronous consensus, which previously no one believed it could be practical. Now we see more and more actual deployment in the real world, just making smarter or more sophisticated use of digital signatures. Before the end of my talk, I would like to bring up something we recently been working on, and I think also relevant to call for the general attention. So we have all kinds of internet services, but the only thing we have end-to-end security is actually messaging. That's the only thing we have. When you think about the blockchain setting, how do you properly manage your digital asset? How do you share your data confidently with your collaborator? How do you even do the actual general online collaboration? Currently, we don't really have an end-to-end secure protection mechanism. Hopefully, our two recent work can motivate the community to look into this problem more seriously, and we can make our internet in general a more safer place. Also, thank you for all the blockchain foundations who supported our research. Thank you.